Saxon Advanced Mathematics, lesson 79. You guys, this is a lesson that is going to make you feel so smart. I promise you when you're done. Even when I look at my notes for this, I think, holy smokes, this is a complicated lesson. Okay, what we're going to be talking about in this lesson are complex numbers. So before we get into the snake's pit of what's new, let me recap for you what we already know about complex numbers. One thing I know is that they're spelled with an O and not an A, so sorry. Complex numbers. Complex numbers take the shape of A plus BI. A is the real number, and B is what we call the imaginary number. You can tell it's the imaginary part because it's got that little I. I is the symbol for an imaginary number, and we remember that the way they arise is when we have something like square root of minus 4. We have a minus inside of an even numbered root. That's what makes a complex number happen. We remember that we let I equal the square root of -1, and then we repurpose this as the square root of 4 times -1. And I'm doing this the really long way. We can break it into 2. Square root of 4 is 2. Square root of -1 is I. So this is how we get an imaginary number. It's from having a minus sign inside of an even numbered root. And remember, the definition of an imaginary number is that it can't be found on the number line. That's kind of the ultimate math sin, is that you can't find it on the number line. Gasp, oh no. So this is the way mathematicians deal with it. Now, what we've learned recently is we can graph imaginary numbers. That's perfectly fine. We can do it as rectangular coordinates, which is what we're now calling old school graphing. Second, I feel like we can graph complex numbers as rectangular coordinates. We just use the x-axis for the real part, and we use the y-axis for the imaginary part. Right? That's easy. We just rename the axes and it works out fine. And we also learned fairly recently that we can graph them also as polar coordinates. Now, if we did it quote unquote in normal polar form, like this is what I'm going to call normal polar form. We know that this would be the, sometimes we call it the distance. Sometimes we call this part the hypotenuse. That's this part. This part is the angle, and sometimes we call it the direction. They mean the same thing, it's just two ways of looking at it. And what we learned is that the numbers mean the same thing, but we write it slightly differently. We write it with this weird little word in here. It's not really a word, it's an abbreviation, right? It's for cosine plus I times the sine of, sorry, I didn't say that right. It's 4 times the cosine of 30 degrees plus I times the sine of 30 degrees. We'll practice doing that in a minute so it'll be clear. This is how we write complex numbers in polar form. Okay, so they look slightly differently, but the meaning is exactly the same as it is for the normal polar, if you will, right? Meaning is the same, it looks quite different. That's kind of off-putting. And a lot of students, including me, kind of cringe at that, but it's okay, we can do it. Now, what if we want to take a a complex number? I was giving you a spoiler there. What if we want to take a complex number and we want to raise it to a power? We can do it. To raise a complex number to a power, we use something really cool. It'll make you feel smart. To raise a complex number to a power, we use Demois Theorem. Of course we do. Demois was a French dude. Second, I want to see if I can find the year that he did his thing. Yes, his name is Abraham Demois. He lived from 1667. A second, I want to take a second to remember him. Abraham Demois. It's one of those French words with a bunch of letters you don't say. He lived from 1667 to 1754. Pretty long for those days, right? He was 87. Yes. Okay. And he was a French refugee who lived in London. And what I like about this is I like to think of this dusty man grinding away up in some, tiny apartment over a fish shop or something, grinding through his numbers all his life, feeling probably somewhat alone and misunderstood. And here, almost 300 years after his death, 270 years after his death, we're talking about him. He's alive and well and we're studying his theories. Oh my gosh, I think that's really exciting and fun. And I like to think that he is smiling down from heaven, getting a kick out of us studying his theorem. Okay, so Demois' theorem, what the heck is it? Well, what it is that if you take a number, it has to be in polar form, right? This is the polar form of a complex number. Has to be polar. And you want to raise it to a power, right? We're raising the whole quantity to a power. The way that you calculate that is that you take this part, the distance or the hypotenuse, and you raise that to the power. And then you multiply the angle. Oh wait, this should be an n. Sorry, my bad. I was using my example. No, I wrote it wrong in my notes. Here we go, like this. Okay, so this is the polar form of the number. You want to raise it to a power. You raise the angle to the power, and then you multiply, I'm sorry, that's not the angle, that's the direction. You multiply this number, you actually take the exponent of this number, and then you take this number and multiply it by the angle. That's what I'm doing here. Okay, let's do an example right away because I said that terribly. Sometimes my brain just doesn't want to think in words, it just wants to do the numbers. Here's an example. 2 cis 30 degrees. We want to raise that to the 5th power. Why would you want to raise a complex number to the 5th power? I don't know, but let's just practice the mechanics of it. So what we do is we change this so that it's 2 to the 5th. And then we multiply the 5 times the 30 degrees. 2 easy steps. 2 to the 5th. Okay, let's count that out. 2, 4, 8, 16, 32. We just keep doubling it, right? So this becomes 32 cis. And then we multiply these two together, 150 degrees. Final answer. Oh, that's not so bad, is it? Why would you want to calculate the 5th power of this complex number? I don't know. But again, we can do it, and that's right. All right, cool. Let's do another one that has a slight wrinkle in it. Of course it does, right? Why would we want to do an easy problem twice? John's going to provide us some drama. It's actually sunny today, so I have to have my sun shield up. Okay, example 79.2. What we are asked to do is use Demois Theorem to find 1 plus I to the 13th power. Express the answer in rectangular form. Okay, well, we'll worry about that later. But what we have to do is figure out how to get this ready, because this isn't in the proper form, right? This is rectangular form. And our friend, the French refugee living in London, he requires polar, right? We have to get it in polar coordinates before we can use his theorem. So this needs to be fixed. The way that we change from rectangular to polar, which we've been doing for a long time, so we're familiar with it, and actually this problem is so easy it looks hard. We're gonna plot this out and figure out what the polar coordinates are. So I know that it's gonna be in the first quadrant because it's 1 and 1, right? There's an invisible 1 there. Okay, we don't need to worry about this 13 yet. That we're raising it to that power, but we don't need that to draw the triangle. What I know is that I want to go 1 unit this way, and then I want to go 1 unit this way. Okay, so I'm not doing this according to the blue lines. I'm just making up my own grid. Right there is our point, right? Because this is the reals, and this is the imaginary. So it's 1 on the reals plus 1 on the imaginary. There's my point. I draw a line back to the origin, and then I go straight down. Okay, great. We know that, I'm gonna move the 1 over here just so I can see it against my triangle. We know these two sides, what we need in order to write this in polar coordinates. I'm gonna make the shape of it here. We need something, cis, something. Oh yeah, this is the hypotenuse, and this is the angle. All right, we're very well versed in going back and forth between polar and rectangular and polar. We know that we've got these two sides, so we know that to find the tangent of this, we can use these two sides and tangent to find this, is what I'm trying to say. Okay, so what we're looking for is an angle where the sine is equal to the cosine. And I don't know about you, but I've got one in mind. Let me grab my old friend, the unit circle. And we're looking for an angle in the first quadrant where sine is equal to cosine. Remember, we can think of this as sine over cosine as well as over Arthur. This is one of our trig identities, and we've talked about it before. But what I'm looking for, because my unit circle has sine and cosine, it doesn't have tangent on it, I'm looking for a first quadrant angle where sine is equal to cosine. And look, here it is, 45 degrees, loud and proud. That's what I want. So now I know that theta equals 45 degrees. Beautiful. I like it, don't you? And so that means I can put 45 degrees right up here. All right, now I need to find out my hypotenuse. And I could use, now that I know my angle, I could use sine or cosine. That would actually probably be faster. I could also use Pythagorean, but given that I know this is a 45-degree angle, excuse me, and it's on my trig function list, I can figure that out because I know, for example, that well, I'll just use Pythagorean. We could use sine or cosine, but I'm not going to go through all that. So it's 1 squared plus 1 squared equals h squared. These are each, it's 1 plus 1. 2 equals h squared, and that tells me that h equals the square root of 2. I flipped the sides there at the end. I just like it better that way. All right, beautiful. So now I can put square root of 2 right here. Now we have written our point in polar coordinates. Now we can raise it to the power. So I'm going to do that on the next page. I'm going to copy this to the next page. No, the square root goes on here. And we're raising it to the 13th power, yes. Okay, all of that was just to translate from rectangular to polar. Now we're in polar, we're ready for Demois Theorem to guide our next step. There's our hypotenuse, there's our angle. We want to raise it to a power. Oh, I didn't mean to do this, I meant to write n. And what we do is we raise the hypotenuse to that power. Oh my gosh, I can't stop writing 13. And then we take that number and we multiply it by the angle. All right? Beautiful. Okay. So now what we have to do is we have to calculate the square root of 2 to the 13th power. Okay. And then we have to do 13 times 45. 2 different operations that we have to do to get our bad boy to work, right? Okay. Great. Let's simplify this first. When we're trying to raise a root to a power, it helps if we rewrite this in fractional exponents. So I'm going to write it as 2 to the 1/2 to the 13th. And then I'm going to write it, I'm going to use the power rule and get 2 to the 13 over 2. We multiply, right? When we're using the power rule. Now, 2 to the 13 over 2, I'm going to split that apart. It's going to be 2 to the 12 over 2 times 2 to the 1/2. This I can simplify. This is 2 to the 6th. And let's do that. 2, 4, 8, 16, 32, 64. And this, I can't really simplify without using a calculator. I don't want to do that. So we're just going to rewrite that as the square root of 2. That is the value we get for 2 to the 13th. And there's all my work I did. Now, we have to simplify this side. Let's multiply 13 times 45. I'm just using old school multiplication here. (585 degrees). Okay, that's certainly very manageable. But now what we want to do is knock this down to size, right? This has an extra spin in it, so let's subtract 360. And we get 225 degrees. And almost there. Now we know those are our two pieces, so we can rewrite our polar form. 64 square root of 2 cis 225 degrees. Beautiful. Okay, that's the angle we get. That's the imaginary number we get when we take this imaginary number and raise it to the 13th power. The only thing we have left to do is put this back into rectangular form, right? We had to put it in polar form to do the calculation, and now John is asking us to shove it back into rectangular. Now the good news is that we can use a shorter calculation. We don't have to draw the angle and calculate, we don't have to draw the triangle and calculate cosine and sine the way we used to. We now can use our unit circle to figure it out more quickly, and I'll show you how we do that. We remember that what this means, I'm going to write it out for you, and you'll learn to do this in your brain. I want to put that number there. We're going to take this number, we're going to multiply it by the cosine of 225, and then we're going to add it to I times the sine of 225. That's what this means. This times the cosine of that plus I times the sine of that. So using our unit circles, it's really easy because we can find this super, super easy. The cosine of 225 degrees, I just go on here, I look for 225 degrees, here it is down here, right? The cosine is minus square root of 2 over 2, and I just happen to notice, oh look, sine is exactly the same. So it's minus square root of 2 over 2 plus I times, okay, sine of 225 is exactly the same, minus square root of 2 over 2. All right. Now we just need to multiply these out. I'm going to slide this up so it's not in the side. Now we just need to multiply these out. So I get 64 times the square root of 2 times minus square root of 2 over 2 plus I times the same thing, right? I'm just writing this out. You could probably see this in your head, but there's so much going on in this problem already that I don't want to confuse you, right? So I just multiply, I just distributed this times this times this. I've written it all together so we can see how the simplification is going to work because it's kind of cool. The two pieces of the numerator multiply together to make 2, right? Square root of 2 times square root of 2, and they cancel against the bottom. So all that we have left are the minus sign and the 64, right? Square root of 2 times square root of 2 go together to cancel against that too. So I'm going to draw a line through all of these. That's going to be part of my answer. Same thing happens over here. I'm going to keep the I, and I'm going to keep the 64, and I'm going to keep that minus sign. But these two square roots of 2 multiply together to make 2. They cancel against this 2. This all goes away. Okay? So my final answer is, I'll write it up here, minus 64 plus I, no, the plus turns to a minus, so it's minus 64I. That is our final answer. And I better draw a nice arrow that takes me up there. Okay, so this is the rectangular coordinate of this number raised to the 13th power. Who knew? I didn't know, but I feel smart that I can go through all of that. Okay, so that's how we take numbers that are complex and we raise them to a power. We use Demois Theorem thusly. Now, what if we want to go in the other direction? What if we have a complex number and we want to take a root of it? Let's look at that. If I was a student right now, I would be saying, I already feel smart enough. You don't have to tell me anymore to make me feel even smarter. I feel just smartly fine. Thank you very much. Stop. But I have more. Okay, so what we're going to do in this example is we're kind of going to use Demois Theorem in reverse. All right, so let me write it down again. See if I can get it right this time. Right? Here's our hypotenuse, here's our angle, there's the power we're trying to raise it to. We raise the hypotenuse to that power, and then we multiply the power times the angle. Okay, let's just jump right in. 79.3. John asks us to find the 4 fourth roots of 16 cis 60 degrees. Okay, so there are now, if I asked you to find the fourth roots of, say, 64, that would be, wait, 64 is not a good number, is it? 16. Let's make it 16. That'll be easier. You would say, oh, well, it's 2 and negative 2, right? Because we only have 2 fourth roots of this number, but because we're doing complex numbers, not just real numbers, we have more roots, and there will always be as many options as there are roots that we're taking, right? So we'll have 2 square roots, or 3 cube roots, or 4 fourth roots, or 5 fifth roots. The numbers will always match, and we'll quickly see that it's fine, it's not hard. But it's different than when we just have real numbers. There we usually just have 1 or 2 roots. But with complex numbers, we have more of them. The number we're trying to find the fourth root of is, find the 4 fourth roots of, here we go, 16 cis 60 degrees. Check your answers by multiplying. That's kind of a one-time thing that John's going to have us do for this first problem, and that's kind of cool. Okay, so how do we figure this out? We use this in reverse. Okay, so first we find the first root by applying this directly. So we would take we'd find the fourth root of 16, and then we would divide 60 by 4, right? That's this in the opposite. Okay, the fourth root of 16, oh, well, we just figured that out. It is positive 2. We just take 2. And then 60 divided by 4 is 15 degrees. So there it is. There's our first root. Now we have to find the additional roots. And this rule that I'm going to give you works whether you're finding fourth roots or sixth roots or 45th roots, it doesn't matter. To find the additional roots, you divide 360 by the number of roots we're finding, in this case it's 4, and then we add that number to the angle. And you'll see what I mean. Words always make it sound harder. Okay, so in our case, a number that we're going to add is 360 divided by 4, because we're finding 4th roots. So that means we're going to add 90 degrees to our angle. So this is the first root. So then, and this number stays the same. Okay, so I'm making a list here of all of my 4th roots. This was my work to find the first one. Here's my work to find the additional ones. Now I'm going to add 90 to my angle. So then it would become 105 degrees and 195 degrees and 285 degrees. Okay, beautiful. These are the answers to our problem. Notice that it worked out so that all of these angles fall within the first 360. That will always be the case. Just because of the way we're doing this calculation, we will never go over 360. Notice if I added 90 one more time, I would be at 375. Too big. So this calculation is set up so that our angles will all fall within the first 360 degrees. We don't have to think about it or worry about it. Now what I'm going to do is I'm going to copy our answers to the top of the next page, and then we're going to actually check these by using the value of our, we don't even need the unit circle. So let me copy these to the top of the next page, and I'll show you how we check them. And that's kind of cool because it makes everything happy. Okay, our first answer was 2 cis 15 degrees. Then we started adding 90, didn't we? Okay, those were the answers we calculated. Then we know that this is Demois Theorem. We're going to use this to check. Okay, and we're raising all of these. These were 4th roots, so we're raising all of these to the 4th power. Okay, that's what we're doing. We're working backwards to check our answer. So we said all four of these roots, all 4 of these are 4th roots of our original expression, which was our original numbers right here. 16 cis 60 degrees. So I'm going to write that at the top, or I'll put it here. That's what we're shooting for. So if we did it right, all 4 of these numbers raised to the 4th power should equal this. Well, we know that we take this 4 and we actually calculate the exponent of that, right? Because that's what this tells us here. So that would be 2 to the 4th, which is 2, 4, 8, 16. So all of these are 2 to the 4th, so I can just write 16s all the way down the list, right? And then let's go to the first one. Now I take this and I multiply it by this. 4 times 15 is 60 degrees. Okay, we hit that one. This time, 4 times 105 is 420. Yes. But when I subtract 360, there's my 60 degrees. This one works. 4 times 195, I better write that one down. 36. 7, not 8. 780. Now I'm going to multiply 2, I'm going to subtract out 2 spins. 360 times 2, 720. And look what we get. 60 degrees again. This one's right. And then here, we'll multiply 285 times 4. 32. 8, 9, 10, 11. An 1140. And here, we'll add 360 to this to subtract out 3 spins. That would be a 1080. Oh, I'm sorry, this is a minus, not an equals. 1080. And let's do 1180 minus 10. Sorry, my mouth is not working today, but my numbers are coming out just fine. When we subtract that, we get, once again, 60 degrees. So we can check our work with these. When we find roots, we can expand them back up by the same power and make sure that they all equal this number. That's how we prove that they're roots. Just like when we have simpler numbers. See how I proved that these all equal that? That's exactly what we were doing right here. We're taking the number that we think is a root and we're checking to make sure that it actually works. And guess what? It did. Yay! You think we're done, don't you? But we're not. We have a couple more to do, a couple more problems. They're not as long as that one. There's a total of 7, but like I said, they're going to go way faster. Okay, find 5 fifth roots of I. Well, okay, we know that we need to get this number into polar form before we can actually calculate the roots. But before we get it into polar form, we have to get it in rectangular form because this isn't even rectangular form, is it? But we can figure it out. We know that it has to be a plus b times I, right? And if all we have is an I, then it's 0 plus 1i. Okay, and we can graph that just to kind of make sense of it a little bit. It's 0 on this axis. This is the reals. This is the imaginaries. And it's 1i, right? So to make it look kind of like a triangle, we could go like that. But it's this point right here, isn't it, that we're trying to find. So how do we write that in polar form? This is rectangular. How do we write this in polar form? Okay, well, it's the hypotenuse, 1, cis, the angle. Oh, that's easy, it's 90 degrees. Okay, so getting this into polar form, when John gives us these random little numbers, and he's gonna give us some other little random number ones. It's not as hard as you think it is. Just draw a picture and think logically about it, and don't let it freak you out. Okay, so now this is what we're trying to break down, right? So we know that that's an n. I have a terrible time. I always want to put numbers in there. So what we're going to do for our first root is we're going to take the 5th root of 1. We're going to do this in reverse, right? And then we're going to take the angle and divide it by the power that we're using. So there's the first one. Now I'm going to simplify that, and it is 1. The 5th root of 1 is 1. And let's see, 90 divided by 5 is 18. There's our first root. Now, to find the additional roots, we take 360 divided by the number of roots we're finding, 5, and then we're going to add that number to this each time. 360 divided by 5 is 72. I've done that enough times. I know it by heart. You could easily divide it out if you needed to, right? Okay, so now we're going to start adding 72 to this. So our second root, remember this number is always the same, and that is 90 degrees. Add 72 again. Add 72 again, that's what, 234. I'm just adding these in my head, but you could easily just add them here. And then one more time. And this would be what, 306. 306, okay? There are our 5 fifth roots. If we wanted, we could check them. Just like we did last time. But you can trust me, these are the right roots. That's a lot easier than the last problem we just did, isn't it? That was a beast. Okay, that's 79.4. Let's try another one that's similar to this one. Not so long. $79.5. Find the 2 square roots of 1. Again, we know we need to put this into A plus BI format first. 1 is the real number, and there's no imaginary number. So there's that. Then we have to put that into polars, which we can do if we just do a quick graph. It's 1 on the reals and 0 on the imaginary. So it's a point like right there, isn't it? Okay, I kind of imagine it a little triangle. Okay, so if we want to write this as a polar coordinate, we would write the hypotenuse length is 1 cis, and it's 0 degrees, isn't it? Because it's right on that axis. Okay, beautiful. So there's 1 cis, 0 degrees. Now what we want to do is we want to take, to find the first root, we take the square root of 1 and we divide 0 degrees by 2. So that would be 1 cis 0 degrees. It's the very same thing. Okay, cool. Now for the additionals. We take 360 and we divide it by 2. That equals 180. So we add 180 to 0 and we get 1 cis 180 degrees. And we're done because we only need 2 roots, and we notice if we added it one more time, we'd be at 360, and we don't want to be at 360. We want it to be less than 360. So this is the answer to this one. Oh, well, that's much more manageable, isn't it? Number 6. This is a long lesson. We're almost done. Find 3/3 roots. Whoops. Of -1. Okay, so rectangular form, which you can also refer to as A plus BI. That's the same thing. This is the real number component, so it's -1 plus 0i. And we'll draw a quick picture. See, it's going to be over here, right? It's -1 and 0i, so it's right here. Oops, -1. All right, so we would write that as hypotenuse is -1, cis, all the way over, 180 degrees. Okay? Don't let these little weird numbers freak you out. Once you graph them, you'll see it's super easy to find their polar coordinates. You don't have to do any calculating. You can just look at it and see. Okay. Now we're ready to find the first root. I'm going to take the third root. Oh, I know what I wanted to tell you. When we are writing in polar form, this number is always positive. Because the hypotenuse, and this is the way I remember it, the hypotenuse can never be a negative number. The hypotenuse will always be positive 1, right? So we change this negative into a positive. Always. This number, you can think of it as an absolute value. That usually makes a lot of students' heads go flat. I understand that. Remember, we're measuring the hypotenuse of this angle. That's positive 1. It goes in a negative direction, but the hypotenuse is 1. So we change that. Now we're ready to take our first root. We take the third root of 1, which is 1, and we divide this by 3. 60 degrees. And I'm going to write it. This time I'm going to do it right. I almost did it right. I put an N instead of an S for sis. My brain just won't let up today. Okay, so what I did was the reverse of this, right? I took the angle and I divided it by the number of roots. So 180 divided by 3 is 60. There's our first root. Additional roots, in this case we'll have 2 more. Oh, let me write roots. We take 360, we divide it by 3, that equals 120. That's the number we add on. So it will be 1 cis 180 degrees, and it'll be 1 cis 300. That's the right answer. Again, we could test those by raising each one of these values to the 3rd power. John doesn't ask us to do that, but we know we've got the skills, right? All right, and there's one more. It's even shorter. We're supposed to find the 4 fourth roots. I like to write this down because it reminds me what I'm trying to do here. 4 fourth roots of 42 cis 40 degrees. Well, the good news is it's already in polar coordinates. Remember, we can't use Demois Theorem in rectangular. We have to convert it to polar. This is already in polar. Hallelujah. So now we're ready to find our first root, which would be the 4th root of 42, and then the angle divided by 4. Now, I can do this, but I don't know the 4th root of 42. That is crazy. I have no idea. You have to use your calculator to do this. You have to use the root key, and you'll need to use the one that looks like this, because there isn't a 4th key on your calculator. And you enter 42, because that's the X value. Then you hit that button. And then you enter 1 divided by 4. How does that work? I think you must have to put this in parentheses, right? Because you have to tell it you want it as a 1/4. Oh no, you don't have to do that because it's just a 4. It's a 4th root, sorry. ignore this. 42, that button, 4, that will enter that in as the y value. And what you will get is 2.55. So now we know that the first root is, I'm going to write it here, 2.55 cis 40 divided by 4. Okay, that one I can do, 10 degrees. And then we'll be adding 360 divided by 4 equals 90. They're all going to be 2.55. That front number doesn't change. The hypotenuse stays the same. It's just the angle. And we're going to add 90, so this would be 100. $190 and 280. Double check, make sure I got it right. Yay! These are all right. Now you know how to use Demois Theorem. I think it's always cool when we do something in math with the person's name. Kramer's rule, Demois Theorem, feel smart. There it is. We can now find powers and roots of complex numbers. The end. Goodbye.